All right. So this is going to be a very brief introduction to AI planning. Um, it's going to be only 20 minutes. There's a lot of research that's gone into AI planning, and I have a slide in the end where if you want to know more, you can reach out to those. All right, let's get it going. So AI planning is a long-standing field of AI. It started in 1960s. It's about the task of finding a procedural course of actions for a declarative described systems to reach its goals while optimizing the overall performance measures. It includes initial states of the world, the desired goals, and a set of possible actions. And you want to synthesize a plan that's guaranteed to generate a state which contains the desired goals. Now, the simplest example that will ground the terminology is this logistics or transportation domain, where you have a set of, I guess, trucks, cars, airplanes, and packages. Packages are at some initial state, and the desired goal would be to have those packages move to a destination. The set of possible actions could be load and unload the truck, flying the airplane. Yes. All right. Now, in this case, a plan would be a sequence of actions that will take you from the initial state to the goal state. As I said, a lot of research has gone into AI planning, and AI planning is a very active area of research. Right? Okay, AI planning is everywhere. So AI planning sits well with autonomous systems. In autonomous systems, when you have to achieve something, you have to plan for it ahead of time. There are lots of different examples of AI planning. You can think about AI planning in space, in robotics, in cybersecurity, logistics, dialogue, even scheduling cranes and elevators. And for example, in NASA, where you have to deal with autonomous systems, these operations have to operate over a long period of time in an autonomous way. You may have budget constraints that you have to meet. In addition, you may have to have some guarantees of these operations that you have to deal with. All of these problems, they have three things in common. One is that there is an initial state. Second is that there is a goal state or desired states. And the third is that there are a set of legal actions that will take you from a state to the next state. So there are three approaches to the problem of action selection or control in AI. First is learning. You learn control from experience. Second is programming, so specifying control by hand. And the third is planning, so specify the problem by hand, and then you drive the control automatically. Of course, there's a lot of recent work that will argue about specifying this problem by hand can be done by large language model, but we'll get to that later. Now, planning is a form of general problem solving, and you have to answer three questions. In terms of the models, how do you define and classify the planning problem and its solution, which is a plan? Second, how do you represent this problem? So what is the language? And the third, how do you solve this problem, which is the algorithms? Okay, so what is AI planning? In a classical setting, you are given the following things. You have a finite and discrete state space, S. You're given a known initial state, S0, a set of goals, set of actions, and you have a deterministic transition function that will give you given a state, an action will take you to the next state. And actions have non-negative cost associated with them. Now, the solution would be a sequence of applicable actions that map this initial state as 0 to the goal state, and it's optimal if it minimizes the sum of action costs. Now, in a classical model, you have a transition system that in all but toy examples is way too large to explicitly get represented. So it's therefore, you have to represent it concisely either in a black box implementation or a planning language. I'll tell you more about planning language in this talk. Now, the solution to this planning problem is a transition graph. So you have an initial state, you have a goal, and you actually want to find a path in this transition graph. However, what makes planning problem really hard is that the state space could be huge. In some cases, 10 to the power of 100. And that's not uncommon in a lot of planning problems. And a note on complexity, a complexity of a planning problem is actually p-space, in the simplest case is p-space complete. However, there are many planning algorithms out there that actually solve this problem efficiently. And how do they do it? The most efficient way to solve a planning problem is through search or state space search. There's a lot of literature on state space search, and it can roughly be broken down into two parts. Local search, algorithms such as hill climbing falls into that category, or global search, algorithms such as depth first search or breadth first search fall into that category. Now you can have blind search, which means that you only have two things: successor state function, which will, given a state, will produce all the successors of that state, and a goal test function, which given a state will tell you whether or not that state is a goal state or not. In a non-blind algorithm or informed search, in addition to those two, you have heuristics. Now, for example, here in this graph, you have a heuristic function that will estimate the distance to the goal, how far ahead you are in terms of achieving the goal state. Now, as an example, A star is a global search, informed search technique that if you're given an admissible heuristic, which basically you would not overestimate the distance to the goal, you're guaranteed to find an optimal plan or guarantees optimality. So as I said, we have to represent the planning language in a concise way. One of the languages is called strips. There's another language called ADL. And here's the strip. In a strip planning task, you have 5 things: finite set of atoms, F, a finite set of operators, where each operator have a precondition, add effect, and a delete list. You can execute an action only if its precondition is met. Once you execute an action, then the add effects of that action is added to your state, and the delete effects of that action is removed from your state. Actions have operator costs associated with them. You have an initial state, I, and a goal description, G. A plan would be a sequence of applicable actions that map the initial state to the goal state. Now, strip is a very, simple, but yet very expressive language. What I showed in the previous chart, and with all the blues that you may have noticed, those are the things that if you relax, you will get beyond classical planning problem. So there are things such as action dynamics. So if you have a deterministic action dynamic, you have full observability and the horizon is finite, you get a classical planning problem. If your action dynamic is non-deterministic, you have a non-deterministic planning problem. Similarly, if the action dynamics is probabilistic, you have a probabilistic planning problem. Moreover, you can have temporal planning where your actions have durations associated with them. You can have hierarchical task network or HTN planning, where the action dynamic is hierarchical. In terms of observability, you can have full observability with non-deterministic planning, and that's where you get a fond planning problem, or you can have partial observability or POMMD, and much more. In terms of computation problem, it depends on what you want to get. In the most simplest case, actions have costs associated with them, and you just want to find one plan that minimizes the summed operator cost, and that's where you have cost optimal planning. If you want to just find a plan and cheaper plan is better, that's where you are in satisfying planning. That's satisficing planning. In agile, quicker is better. You want to find a plan as quick as possible. Now, in some other cases, in addition to just finding one plan, you may want to find multiple plans. And there are many settings for when you actually would be interested in finding multiple plans, such as plan repair, plan execution, plan failure. It may also be that you have some preferences or criteria that are not necessarily expressed in your domain description. And furthermore, it could be that the domain is actually under-specified or is incorrect. So getting multiple plans would be ideal in those situations. And in that case, you have top K planning, where you want to find K plans that no cheaper plan exists. Here, K has to be given to you. In cases where K is unknown, but you have a cost bound, you are operating under top quality planning. So you want to find all plans up to a certain cost limit. And finally, diverse planning, where you have some diversity metric in hand, as well as a quality metric. So you want to find as many diverse plans as possible in your problem space. There are many, many planners out there. I'm only naming a few here. So if you don't see yours, it's just probably there. It's just not mentioned here. Fast forward is probably the most known, in addition to fast downward, where these are originally classical plannings, but there are many, many versions of them available that are built on top of those, such as numeric, conformant, contingent planning. And in fast downward, you have OSP version or oversubscription version, you have a fund version of it, you have a probabilistic or temporal version of it, and so on. SHOP2 is an HTN planning. LPG is a diverse planning. Also, there are, I guess, multiple versions of it available. Fund planner, PRP, is the most popular fund planner. Oversubscription planning, and there are many, as well as the planners that find multiple plans, and those would be top K planners, or a collection of 4-bit iterative planners, diverse, top quality, and so on. So here's sort of a general framework for a planning and planning in use. There are 3 components or 3 problems that you have to solve. The first problem is the problem of model acquisition, sometimes known as knowledge engineering problem. And it's about the problem of, okay, we have data, and this data, by the way, now these days is in the form of natural language. And you want to find input to the planning model. An input to the planning model is that most planners now take in is PDDL, or planning domain definition language. So how do you go from data or natural language to a language where the planners operate on? The second problem is the actual planning, or how do you efficiently find solutions to this problem? In some cases, you want to find one plan. In some cases, you want to find multiple plans, and so on. And the third is this sort of loop of planning and execution, where you may, in some cases, even adjust your model based on the feedback you receive. And in some cases, you really need to, maybe replan from where you are, updated state, and go back to this loop of calling the planner again, getting plans, and so on. Traditionally, the model acquisition or knowledge engineering has been studied in the KR community. Planning has been studied in the ICAPS community, and execution was probably most popular in the robotics community. And now it's all somewhat interleaved. Now, let me spend just a few minutes on what I just talked about, which is PDDL, or Planning Domain Definition Language. I should say there are other planning languages, such as RDDL and HDDL. So those are representations for hierarchical task network planning, as well as probabilistic planning. But here, I'm just going to talk about PDDL. It was originally was proposed for international planning competition, which happens somewhat every 2 years at ICAPS community. And it's meant to be a standard language where all the planners will get as an input and can operate on. PDDL can represent strips, which is a planning language that I mentioned earlier, as well as ADL. In PDDL, you have two files, the problem file and the domain file. The problem file is on the left, defines the initial states, the objects. So here we have 4 passengers. By the way, this is Myconic elevator domain. So you have 4 passengers and 8 floors. The problem file describes the different floors, the relationship between the floors, and the original location of the passengers, as well as the goal. The goal would be to serve these passengers, so move them from initial location of them in the different floors that they are to a final destination floor. The domain file describes the predicates as well as actions. So here, some actions would be board a passenger into an elevator, or depart, as well as the movement of the elevator, which is going up and down. In many of the planning problems, you have a generator. So here in this case, you only have 4 passengers and 8 floors, but there's a generator for Myconic where you can generate many different versions of the same domain. So the domain would generally be fixed, but the problem file can vary based on running this generator and getting multiple different versions of this problem file. The planner, once you give it these 2 files, will produce a plan. The plan is on the right, which would be a sequence of actions that will take you from the initial state to the goal state. So that means that the goal definition in the problem file would now be satisfied by executing the plan on the right. So if you want to find out more, again, this was a very, very brief tutorial. We've given tutorials on AI planning in the past. You can look at some of those that I highlighted. So planning theory and practice was given at AAAI 2022. There's also a tutorial we gave last year at ICAPS that's all about finding multiple plans. I only just highlighted a few of those problems, such as top K planning, diverse planning, or top quality planning, and that tutorial will give you much depth into those problems. And as I said, there are many, many planners out there. Here, I'm just outlining some of them, and they are available on GitHub for you to use. Okay, and then that's it. I'll take questions. Thank you. Any questions? Yes.
So I'm not an AI planning expert, and when you introduced the STRIPS framework, you mentioned there were alternatives, but it won out. Why is it?
Why is it? Well, I guess probably history. STRIPS was originally meant for the the robots from SRI, and it will have some limitations, and ADL would be much more complicated or much more complex. And it depends, I guess, if you're looking for more simple way, you go with strips. And if you want more expressivity, perhaps you go with ADL. But I don't know whether probably that answers your question or not, but I guess I would say that.
So more, there are languages that support more features, and there are fewer planners that support more features. It's much easier to support strips than support graph predicates. There are planners that support almost any feature.
Any other questions? If not, we'll move on to the next section. Thank you.
Maybe I have a question. If you talk only about the grid space, the any plans for grid space?
Continuous space.
Yeah. So there's extensions to temporal planning and with continuous numeric variables, continuous change, there's
The month, many.
events, and there's 17 different variants of how you can do that. Then, of course, like Shirin said before about ADL, the more expressive you make the problem, the less planners actually support it.
All right.